So hi everyone, I'm Agnieszka from the University of Warsaw from Poland, and today I'll talk about duplication episode clustering in phylogenetic networks. Gene applications, especially the large-scale events such as whole genome duplications, have had a major impact on genome evolution. So identifying when and where such events occurred can help us understand how new functions or any biological innovations arise. And in this talk, I will show how our method can be used to detect and validate whole genome duplications. But let's start from the beginning. One of the standard methods for detecting gene duplications is tree reconciliation method. And in this method, by mapping nodes from the gene tree, I guess I don't have a pointer, but by mapping nodes from the gene tree to the nodes from its species tree, we can infer the locations where the duplications have occurred during evolution. And here we omit the mapping of the leaves, but as you can probably guess, the genes A1 and A2 are mapped to species A, B1 and B2 to species B, and so on. So we say that a node is a duplication if this particular node, and at least one of its children are mapped to the same node in the species tree. And such a mapping can be represented as an embedding of the gene tree into the species tree. Here we can see where the gene duplications occurred, and such an embedding, we call it an evolutionary scenario. Tree reconciliation is a widely used method, but it assumes only a tree-like evolution, which is a bit limiting. And actually, in phylogenetics, we usually, I think, use phylogenetic trees, while evolution, in a lot of cases, involves processes like horizontal gene transfers or introgression or hybridization. So we need some more complicated models for such processes. So we need phylogenetic networks. And like I said, tree reconciliation is defined only for gene trees. So to overcome this limitation, we used the network unfolding method, which transforms phylogenetic network to a semi-binary tree. And what's important, this transformation ensures that the evolutionary the evolution that is encoded in this data is preserved. So there is a one-to-one correspondence between the paths from the root to the leaves from the original network. There's a one-to-one correspondence to the paths in the unfolded network. So after we unfold the network, we can apply the tree reconciliation without any further changes. And for this example, here we have a gene tree and the unfolded network. Here we have two possible mappings, which differ only in the mapping of the root of the gene tree and of the B node. As you can see, the B node is mapped to B1 or to B2 in the second mapping. And if we look at the evolutionary scenarios that correspond to those mapping, you can see how the gene trees are embedded in the network. In both of these scenarios, the duplication is above the node C, but the placement of the root of the gene tree is different. So now let's move on to the core of our method, that is the duplication episode clustering. When reconciling multiple gene trees with a species network, gene duplications often appear near each other or even in the same location. And sometimes it is possible to slightly adjust the placement of a specific duplication by moving it towards the root in order to cluster, to group the duplications more effectively. And it allows us to identify said duplication episodes, that is specific nodes in phylogenetic networks in which multiple gene duplications are thought to have occurred together, possibly reflecting some larger event, for example, the whole genome duplication. And of course, this this approach is not arbitrary. The moving the duplications is not arbitrary. We have to preserve, of course, the time consistency, and we cannot create new duplications during the process. So we can move the duplication only if it's biologically meaningful. So technically, we can move the duplication towards the root until we meet a speciation node. On this example, we have on the left we have the original embeddings, and to the right we move the duplications up. So this method gives us it allows us to move the duplications, to consolidate the duplication signal when it's appropriate, but it still preserves the reconciliation constraints and the evolutionary signal that it's encoded in the data. And we defined two problems that can be addressed with this method, NetEC and NetFees. The goal of NetEC is to find a minimal set of duplication episodes that can explain all the duplications that are observed in the given set of gene trees, and it's probably NP complete. The problem is probably NP complete, but we didn't prove it yet. And we have the heuristic algorithm for this problem. The NetFees problem, on the other hand, is a validation problem. Here we are given the set of candidate duplication episodes, and we ask a question if the observed duplications can be explained by only these given episodes. And for so this problem can the algorithm that solves this problem can help validate some hypotheses about the evolution and the whole genome duplications. And for this problem, we have a polynomial time algorithm which uses the Łukasiewicz free-valued logic. Now let me show you a short example of how the algorithm for the problem, for the NetFees problem, can be used. We applied this algorithm to over 2,000 gene trees and the phylogenetic network with species from the Pandanalis clade. And this network, there are two reticulations in this network, as you can see, and with those orange stars, it's barely visible. So sorry about that. Well, I'll show you the last picture because you can see something here, but sorry for that. So by the orange stars, which are visible, we mark the whole genome duplication events that were postulated by Shi and colleagues in their work about Pandanales. And our goal was to check whether we will be able to validate those whole genome duplications, and if they will be sufficient to explain all the duplications that can be observed in this data set. And the results show the support for 3 of the 5 whole genome duplications, and we were not able to recover the 2 of them. So I don't have a pointer, but if you look at the left of the drawing, you can see the unsupported one, the unsupported whole genome duplication. Here, probably the duplications have been pushed towards the root because of the due to the properties of the algorithm, and making it impossible to recover the duplication signal. And in the case of the duplication with the 4 next to it, well, here, if we assume that there was a whole genome duplication, the signal might have been lowered by, for example, gene losses, which usually occur after the whole genome duplications, or maybe the signal was not that good because of the reticulation that is nearby. So, as you can see, the method can be used to detect, validate, or challenge postulated whole genome duplications. We defined two problems using this clustering method, and we are now, since this is the work in progress, we are now focusing on assessing the accuracy of our method. So we plan to conduct a lot of experiments on real data and also on simulated data sets. And we also want to investigate maybe some other clustering approaches that would maybe perform better in complex and ambiguous networks like the one that you have seen on in the example. So if someone is interested, our work, the data sets and the algorithms are at our Bitbucket. It's publicly available. And I would like to thank my co-authors and thank you all for the attention.
Okay, thank you. That was a wonderful talk. Are there any questions? We have plenty of time.
Hello. Thank you for the very nice talk. I had a question on the unfolding procedure of your tree.
Unfolding, yeah?
Yeah, the unfolding.
Yes.
And does it work well also if the convergent branches are very far up the trees and far up the tree? I'm wondering if the size of your tree might not blow up after the unfolding procedure.
No, it's a standard, I would say, procedure, and it was proven that it works for all the networks.
Okay. Well then.
So I actually have a question since I'm not seeing hands. Are you using dated trees or is this purely on topology?
No, it's purely on topology, and the dated trees are not so easy to get. So yeah, it's only topology right now.
It's understandable.
But maybe we will do some extensions.
Are there any other questions?
So in your presentation, you're looking at the way you presented it. You're looking at networks as a representation of horizontal gene flow. Networks can also represent uncertainty, and I wonder if you've thought at all about using that representation and then using that information to say something about certainty about the events that you infer.
Yeah, I think it can be done. I mean, like I said, it's a work in progress, and we want to test it on various data sets. So maybe we will do, as you said, so to not only focus on the biological events that we know of, but only on the uncertainties to check what the results will be. Thank you.
Thank you for the nice talk. In the case where you're detecting the whole genome duplication, then are you assuming that all the duplications stem from whole genome duplication, or how do you cope with like the occasional also small scale duplications?
Yeah, so as you could see on the last picture, sometimes we can cluster. We cluster only, for example, 4 duplications. So this indicates that it was not a large-scale event, and we can say freely that it wasn't such an event. These were only single applications which clustered by accident, let's say.
More like the interpretation.
Yes, it's about the interpretation.
So if you can go back to the unfolding operation again, sorry to insist on that.
I'm so sorry, my throat
in,
isn't cooperating.
Is there any particular order in which you perform these unfolding operations?
No, if I remember correctly, no.
So you
No, sorry. I think it's sorry. It's an algorithm that I used. I can't remember right now, but I think it's. Well, I have to check. I'm so sorry.
Thank you.
I jumped the gun, so Danny.
It's okay.
Oh.
So maybe I don't understand correctly, but if you move the gene duplications up, you also add a lot of gene loss. Do you then not keep the assumption of parsimony, or how do you reflect on that?
Sorry. Come again. I didn't get that.
So if you move the gene duplications up the gene tree, are you not also adding a lot of gene loss? And then how does that reflect in your parsimonious assumption, or how do you
Sure.
see
Yes,
that?
we add a lot of gene losses, but in this definition of the problem, we don't count the gene losses, and it's a huge problem. I agree, and in the future we want to change that, but the algorithm for that would take into account the gene losses would be much more complicated. So we started with that approach to see what the results will, what results we can get, and then we will expand it with the gene losses, because the gene losses are very important in the topic of the whole genome duplications, because there are a lot of them after the event. So we will take them into account. So that's valid question.
I think we have time for one more question, if anyone has one. Well, thank you so much.
Thank you again.